My name is Immanuel Bloch. I'm one of the scientific directors at the Max Planck Institute of Quantum Optics in Garching, close to Munich, and also professor at Ludwig Maximilians University in Munich. And I'm the coordinator of the PASQuant's project of the Quantum Flagship, EU Quantum Flagship project. So we're very excited to start the project with fantastic project partners, and I think what we've already seen in the first year is like tremendous advancement on the control capabilities and system sizes that could be realized, I think even a little bit beyond what we had hoped for initially. The team is on the experimental side working on several applications in material science and also on optimization problems. And there have been actually tremendous advancements in the context of material science simulations, both on the simulation of strongly correlated electronic systems, which for example play an important role in the context of superconducting materials or quantum magnets. And in the context of magnetism, quantum magnetism, actually there was a lot of very nice results in simulating quantum magnets in higher dimensions, which are extremely hard to compute on classical computers. On the theory side, there have been actually a lot of interesting developments on how to extend the reach of the PASQuant's team, how to find new application areas beyond kind of what we had on the radar on the experiment so far. So I think we want to continue extending the capabilities of the quantum simulators, trying to reach out more and more to applications where we have really hard to simulate problems, trying to reach a so-called quantum advantage, or at least drive the systems into regimes where we can deliver useful qualitative and quantitative input, which allows us also to advance some of the best classical numerical methods and compete with these. So I think this is a close interaction between both competition between classical numerics and the quantum simulators that we now have in the lab, and learning from each other in extending the capabilities of both systems to the benefit of, being able to handle, let's say, numerically much better materials, either through simulation approach, quantum simulation approach, or through classical numerics that we advance by this. There have been many of these moments, but it's like each time you have a breakthrough result in the lab, or you stand there in the lab, and I still remember times, when I was doing measurements myself at 2 o'clock in the night or 3 o'clock in the night, you're working hard the whole day long to achieve the result, and suddenly you see for the first time things working out. And these can be discoveries or events that nobody in the world has seen before, and this is a little bit of a really discovery moment that you can have, and that's I think for a scientist the most exciting moments you can have in your scientific career. They're really fun, they're really enjoying, and the excitement, then all the hard work that you've been working for months or years suddenly pay off, and those are wonderful moments as a scientist.